All right. Good morning again, everyone. I hope you can hear me well. Kumusta naman kayo today? Tapos na ba kayo mag-reg? Try opening my camera. Or busy pa rin kayo paghanap ng klase, paghanap ng teachers? Okay, wala talagang gusto mag-share. That's okay. So you guys can speak up. We can spend the first 5 minutes just catching up with each other para alam ko rin yung nangyayari sa inyo. So, how's everything so far? Adjusted na ba kayo uli um, sa online setup? Okay, good for you. So tapos na kayo sa Reg. How about enrolling in Canvas, joining the teams? Anyone having any trouble with that? Yun pala, I watched portions of the recording of the sessions last time. Ang dami ko palang lag putol-putol. So please let me know kung napuputol ako mid-sentence tas hindi na kompleto yung thought. Actually, now I subscribe to a prepaid internet subscription. Naka-data ako ngayon. Hopefully, this is better than my Wi-Fi. Kasi problema, pag yung mga gadgets sa bahay nakakonect sa Wi-Fi, sabay-sabay kayong gumagamit, mababa yung bandwidth. So hopefully, I'm getting across well or better right now. So just let me know kung medyo napuputol ako mid-sentence or nawawala talaga. So I can repeat those salient points that I might have missed. Okay, so I'm sorry to hear that sabi ni Miguel may mga klase na nag-overlap. I don't know about that supposedly kasi dapat sa atin yung time slot na 11:30 to 12:30. That's why I didn't want to schedule a different time, a different meeting for us on a different time para alam ko na sa akin dapat yung 11:30 to 12:30. But if you cannot avoid that, well, that's fine with me. You are not required to attend the synchronous classes, but I guess this is a big plus. So I encourage you to attend. And in case you cannot attend, then pwede kayong manood ng recordings. Yes, Lian, I agree. Mahirap yan palipat-lipat ng LMS. Though the university is pushing for a uniform LMS for all classes. I think they'll try to implement it in the second semester, but I don't know how well will it be implemented kasi laging academic freedom, laging may labay amay. I mean, there's always a battle between administrative decisions and academic freedom. So let's see ano yung mangyayari. But we'll try to, I think the math division will try to use Canvas in the near future. So hopefully next semester para isa na lang yung lalaginan tapos unified yung calendar. Yeah, so hopefully within the semester you'll get used to it. Kasi alam ko yung iba Google Classroom pa rin, yung iba ay ano ba yung gamit pa ng iba? Google Classroom, Microsoft Teams, and I forgot the other one, Moodle. Yung iba Moodle yung gamit. So, but hopefully we'll be able to adapt to this situation. Facebook pa rin yung iba. So I think some faculty members still use their Facebook. I don't know about Facebook kung gaano siya ka-effective, pero dati Facebook group lang din yung ginagawa ko. Upload ako din ng materials. Ang problema, walang checking. So, hindi ka nakapag-check online via Facebook. So, at least with LMSs like Canvas, we can do grading real time and we can give the feedback as immediate as possible. So, yun pala yung plano ko. I don't know if I mentioned it last time. Hold on, guys. Excuse me for a moment. Di ko maalala kung nabanggit ko or na-propose ko sa inyo last time because for problem sets, I want to grade your problem sets. Tama ba? Problem sets tayo, no? Lab exercises and problem sets. I want to grade all of the problem sets across all lab sections and all lecture sections. What I'll try to do is to divide the problem sets so that yung submission ay per item. So meron kang problem set 1, problem set 1, problem 2. So para maging ganon, kasi hiwa-hiwalay nyo siyang isa-submit sa Canvas. So the nice thing about that setup is you can do retail submissions. So kung number 1 pa lang yung tapos mo, pwede mo na siyang i-upload. Tapos natapos ka sa problem 3, pwede mo na siyang i-upload. And then kung nahirapan ka sa problem 2, pwedeng sa malapit na sa deadline mo siya i-submit. And an advantage for that is para hindi ako matambak, for me, ay para hindi ako matambakan ng chechekan. So when you submit the first problem, kung free ako, I can start grading it and the feedback will be immediate. Para yung comments ko, pwede nyo pa rin ma-incorporate dun sa items na ginagawa nyo, yung ginagawa nyo at that particular moment. So, hindi nyo kailangang antayin na matapos yung buong problem set. You can do retail submissions. And actually, I would love that kasi pwede ko siyang simulan checkan, hindi ako matatambakan sa dulo. And for you, you can use the feedback or the comments I'll put in there para ma-improve yung susunod yung mga submissions. Though I trust you guys na hindi nyo i-share yung tamang sagot o yung comments ko dun sa work nyo pag chinekan ko siya na hindi pa nakapag-submit yung ibang classmates. So I trust that you guys will be upholding the university values of honor and excellence. All right. So I think may questions pa kayo about what we talked about last time? Other suggestions? Or saka na lang talaga kayo makikipag-negosasyon once we have you have seen how the lab exercises or the problem sets look like? So if we are good with housekeeping matters, maybe we can go down into business. And as one of your classmates requested last time, we'll do a quick recap of the things that you might have heard from AMAT 152 na nilagay ko rin as a review chapter in Math 174, which is basically talking about the fundamentals of computing. Again, there is no assigned assessment for this particular topics. It's just that baka mabanggit natin to as we go along the specific topics in the course. And my assumption is this were already covered in AMAT 152, so hindi ko na siya i-discuss in detail. So may mga algorithms that I will talk about convergence. Alin yung mas mabilis mag-converge. And I don't want you to feel na kailangan ko pang i-discuss yung convergence. I am assuming that you already discussed this in AMAT 152, so ina-assume ko na familiar na kayo dun sa mga terms. Medyo marami yung topics because when I was teaching 174 before I left, inaabot ako siguro ng isa or dalawang buwan sa 1.5 months sa fundamentals of computing. But yeah, we'll try to squeeze this in 1 hour or so. So yeah, just bear with me. No, I'll be not very detailed as I would like as I would like to. So yon. Kung may tanong, feel free to put it in the chat, raise your hand, and mute yourself, and I'll be more than happy to address your question. All right. So let me just turn off my camera. Kasi yuyuko din naman ako most of the time para magsulat sa tablet. So let's start. So I hope you guys can see my screen. Let me know if yung mga, lalo na yung mga dumating or nag-join later than the time we started. Kasi minsan may glitch si Teams na hindi nakikita ng mga latecomers yung shared screen. Okay, so I hope I'm back. Hello, guys. Hello, can you hear me?
Yes po, sir.
Pag naputol ako. Okay, thank you. Pero hindi gumagalaw yung slides ko. Hold on. So, okay. Ayan, finally, gumagalaw na siya. Welcome to the Philippines daw sa internet connection. Sorry about that. But yeah.
Sir, are you sharing screen po?
Restart ko lang siya.
Thank you po.
There we go. All right, so as I've mentioned, we'll cover some topics in the fundamentals of computing. So there are three major, actually, how many? We'll talk about errors. We'll talk about the Bachmann-Landau notations and convergence and stability. So basically, four main ideas or central ideas in computing or in mathematical or scientific computing. So I'll try to squeeze this in into the next how many minutes? So 30 minutes or so. But let's try. I have 36 slides, so hopefully marami makover natin. But all of these materials can be found in the work text. I included in module 1, the specific pages where you can find these discussions, all right? So first, we'll look at errors. So of course, whenever you do something in a machine, expected na laging meron dyang kakibat na errors, all right? So whenever you try to implement an algorithm, you try to compute something, unless you do it by hand, and specifically for the purpose of getting the exact answer, we should expect some errors to creep in our calculations, especially if you will be doing machine calculations. Actually, hindi nga lang machine error yung pinanggagalingan ng errors in approximation or in calculations. Of course, there are three major portions, or actually three major types or sources of errors. Disregard na natin yung human errors, so hindi na siya kasama. Pero in a perfect computing device or in a perfect person performing the computations, there are still three major sources of error. And they are, namely, the unavoidable or types of error, unavoidable error, theoretical error, and the round-off error. So I'll briefly describe what these three types of errors pertain to. Pero this is just in general, what is an error? So we usually measure error by in two ways. If your number p hat is an approximation to a number p, then we say that the absolute error is just the absolute difference between the two numbers. Okay? So the absolute error is p minus p hat. So ito yung usual na notion ng error, gaano sila kalayo sa isa't isa. However, usually the absolute error is not a good indication of the accuracy. So pag tiningnan mo lang kasi how far they are with each other, hindi natin masyadong na-describe yung error, because what if you are approximating, say, 1, and the answer that you got is 0.9. And then you say that the absolute error is what? The absolute error is just 0.1, right? However, hindi natin alam kung gaano kalaki yung 0.1 relative to the number that you are approximating. So, halimbawa, you're approximating 1 million. And your estimate for 1 million is, say, 999,999. And so the absolute error for this case of approximation is 1. And then what if you are asked to compare which one is better approximate? Approximating 1 by the value 0.9, or approximating 1 million by the value 999,999. If you will be basing your answer on the absolute error, you'll say, probably the first situation is more accurate, or the first estimation is more accurate kasi yung absolute error niya 0.1 lang compared to 1 in the second case. But actually, you could be wrong, because here, the error in the approximation in the first case is 0.1, but you're approximating 1. So sort of ilang percent yung error. So basically, pwede mo sabihin that the error is 10%. Kasi 0.1 divided by 1, that's 10%. So that's a pretty large error for some applications. Meanwhile, if you say kahit 1 yung absolute error dun sa case number 2, pero yung ini-estimate ko naman ay 1 million, so yung 1 na yon is much more negligible with respect to 1 million than 0.1 with respect to 1. And with that idea, whenever you want to compare the accuracy of a process or an estimation process with two different numbers being compared or being estimated, it's almost always better to talk about relative errors, all right? Because this will take into account the magnitude of the number that you are estimating. So basically, all you need to do is to divide the absolute error by the magnitude of the number being estimated. So itong relative error, you can think of it as a percent error. So whenever we ask you to describe the error in a particular estimation process, I prefer that you give the answer in terms of relative error. Kasi pag sinabi yung relative error po ay 0.27, I don't know how big 0.27 is with respect to the number you are approximating. I hope you will agree that if you say the relative error is 0.01, so that will I hope you agree that that is a better description of the error, because at the back of my mind, I know that the error is just 1%. So usually it's much better to describe the accuracy with relative errors, all right? And this is extremely helpful, especially if you are comparing two algorithms where you are approximating two different numbers, okay? So, lucky din ba sa inyo yung projection? Kasi nagsusulat ako pero nakikita ko sa laptop ko ay delayed yung annotation. So, yeah. Hopefully it gets better along the way. All right. So, okay. So the first type is unavoidable error. So let's see. Unavoidable error is just the error due to the uncertainty of the inputs. Okay. So pag meron kang algorithm, lagi kang may input, right? Meron kang ilalagay dun sa process. Now, if you are uncertain with the values of your input, then however perfect your computing machine is, however perfect your algorithm is, there will always be an error to begin with. Kasi laging yung input mo may problema na, so the output will be uncertain. So that's why we call this the unavoidable error. So this could be thought of as the error in data collection, measurement error when you are taking physical measurements. So yun yung error na hindi na natin kayang baguhin. Because usually in the purview of numerical analysis, we want to improve algorithms, minimize the errors associated with algorithms. We want to have better machines that can calculate with a much higher precision. But those two steps are nothing compared to unavoidable error, because the unavoidable error ay bago ka palang mag-undergo sa process, bago mo palang siya i-input sa computer, meron na palang inherent error yung data. And I called it unavoidable kasi wala na tayong magagawa doon. We just need to accept the fact that there is a measurement error involved or measurement noise involved. So hindi na natin siya kayang tanggalin, but we can take into account that when we interpret our solution. So an example is in approximating or in computing the value of sine x, okay? Now, what if I tell you to approximate the value of sine x, pero ang input ko ay hindi certain? So, halimbawa gusto kong evaluate yung sine x sa x0 naught, sa x0 star. If I want to approximate the value of sine at the point x0 star, dapat ito yung makukuha kong value, right? However, what if I don't have a perfect way of measuring what is x or knowing what is x sub 0 star? So kung hindi ko siya makukuha with exact precision, probably pwedeng ang x0 ay length nung length siya ng isang atom. Length ng atom. Meron bang length ng atom? Or halimbawa, ano siya, isang siyang quantity na gusto kong i-measure, like say, the distance traveled by a particle. All right? Dahil limited yung degree of precision ng measuring device na gagamitin ko. So ibig sabihin uncertain na yung input. My input ranges from x0 minus delta, which is caused by an underestimation of the quantity I want to put into my algorithm, or x of 0 plus delta. So meron ka laging interval of confidence on your measurement. So say meron kang delta na possible error. Okay? So ibig sabihin, ang makukuha kong value ni sin x ay hindi talaga sin x, pero pwedeng ito, sin x minus epsilon. Or I can also get sin x plus epsilon. So kahit perfect yung pagko-compute ko ng sin x, gawin ko siya by hand or using any high precision technique. But since I am uncertain with the input to begin with, the answer that I get will also be uncertain or meron pa rin error na involved. Okay? So that's unavoidable error. Errors due to uncertainty in the input. And as the name implies, any numerical technique or numerical analysis technique cannot get rid of the unavoidable error. Unless makaka-devise tayo ng way to better measure our data beforehand, but usually that is always a physical impossibility. So kaya laging may unavoidable error na involved. All right, so another example is unavoidable error na hindi lamang dahil sa uncertainty ng data, but also based on the problem itself. So for instance, the problem is to find a function whose domain is the set of real numbers, satisfying that f of x is 0 for all integers. So pinaghanap ko kayo ng function f na 0 siya sa mga integers, and the derivative has magnitude less than or equal to 1. And that's the only thing that I ask you to do. Well, you can be clever about it and say, sir, alam ko na sagot dyan, f of x equals 0. Note that f of x equals 0 will satisfy all the conditions set forth in the problem. Okay? However, if I want to be fancy about it, gusto ko magpabida-bida dun sa teacher ko, sir, alam ko ang sagot dyan. Pwedeng 1 over pi times sine pi x. Okay? Now, this second function also satisfies these conditions, all right? But which one of them is correct, right? So kung sabi ko gamitin nyo sa algorithm nyo yung function f that satisfies this one. Some of your classmates will use this. Some of your classmates will use this. So that means we have introduced an unavoidable error into our algorithm because of the uncertainty in the problem or the description of the input. So posibleng merong missing data or missing information leading to different possible answers, which are very much different from each other. So if these are my two answers, then I need to take into account dun sa solution na dun sa solution ng mga estudyante ko dahil may gumamit ng 0, may gumamit ng 1 over pi times sine pi x, and both of them satisfy the premise that I gave them, then there is sort of an unavoidable error in the input, which probably amounts to the absolute difference of the two. Well, this is not a formula, but just an approximation of the unavoidable error. Kasi pwedeng yung sagot nyo ay ito, pwedeng ito rin, or anything in between as long as these two conditions are satisfied. So just a clarification, this is not the usual or the exact amount of unavoidable error. So that's why I said it is around this value, because you get two possible answers and you might get anything in between of them. So kaya around yung ginamit ko, tapos less than or equal to pa dito. So this is just an estimate of what could have been the unavoidable error. And usually in practice, we don't have any way of knowing what the unavoidable error is. Kasi kung alam natin kung ano yung eksaktong unavoidable error, then pwede natin siyang i-avoid. Kasi i-add ko lang siya dun sa final answer or isusubtract ko sa final answer, then I got rid of the unavoidable error, which is absurd kasi tinawag ko nga siyang unavoidable error. Okay? So I think that's a quick introduction to unavoidable error. So simple lang naman siya, no? I hope that's easy to intuitively get. All right? But don't hesitate. If you have any questions, just let me know. Otherwise, I'll go to theoretical error, the second type of error involved in any process. Okay. Now, yung theoretical error naman, sila yung errors dun sa mismong algorithm. So pag nag-design ka kasi ng algorithm that will compute for something, you know that there is a theoretical limitation to it or a mathematical limitation to it. So halimbawa, one classic example is approximating the value of sine pi. Okay? So obviously, we cannot compute sine pi. Actually, we can. We can compute sine pi. Pero kung ipapakompute natin to sa calculators o sa computers, unless ipoprogram ipoprogram natin ng sine pi ay exactly equal to what? Equal siya sa 0. Tama ba? Yeah, sine pi is 0. Now, unless i-specify natin siya na ganun, i-define ko sa code ko na sine pi is equal to 0, the problem is that computers are finite value machines. So, kung magko-code ka ng algorithm sa computer para i-compute yung sine pi, si sine ay isang transcendental function. So, hindi siya kayang isulat as a finite, in terms of a finite arithmetic operations. So, kung gusto mong makuha yung eksaktong value ng sine x dahil hindi algebraic yung sine x, hindi mo siya kayang isulat in a finite number of arithmetical operations. So, actually, the exact value of sine pi in terms of sine x, in terms of elementary functions or arithmetic functions is the Taylor series expansion. If you remember that from Math 38. So, ang sine x ay equals sa summation na to until infinity. So that's the only way that you can get the exact value of sine pi. But again, since computers are finite or we want to develop algorithms that are finite in nature, so ibig sabihin finite lang yung number of operations that we can perform, then what I'll do is instead of summing up to infinity, I'll just take a finite value of n, okay, and see how good the approximation is. So for instance, if you say, okay, konti lang yung computing capability ko, so what if n is equal to 1? So if n is equal to 1, you plug in, you take the sum, plug in k equals 1, and that's it. And what you'll get is f of 1 of x is equal to x. So ang approximation natin sa sine pi ay pi, which is not good because pi is 3.1415 and so on, but we expect sine to be less than 1 or less than or equal to 1. So using only one term in the Taylor series expansion in your algorithm is not enough. So if you go ahead and consider two terms, go to F2, so that means n is set to 2, kinuha ko lang yan, 2. Ang makukuha kong function ay x minus x cubed over 6. So my approximate for sine pi became a little bit better. It is minus 2.0, around minus 2.03, but still not good enough. But if you take 100 terms, if you use n equals 100, then you'll get this approximation. 3.5 times 10 to the minus 16, which is very close to the value that we want. Which is 0, right? Nag-warning si Teams na bad audio quality raw ako. How about from your end? Narinig niyo pa ba ako?
Yes po, sir.
Okay naman po, sir.
Hello, guys.
Sir, dinig po.
Dinig po, sir.
Hello. Hopefully I'm back. Sorry about that. How about now? Okay, yeah.
Sir,
Naglilipat
okay.
ako ng okay. Naglilipat ako ng Wi-Fi connection. Tatlo na yung Wi-Fi ko sa bahay. So hopefully mas gumagana na siya ngayon. Pero delayed pa rin yung annotations ko. But anyway, I hope I was able to discuss ano yung nangyari pagka n equals 100, right? But the idea here is if you choose a larger value of n, the Taylor series expansion will give you a better approximation. Okay? Now, the Taylor series expansion is not the only way to approximate the value of sin x. We can use an interpolating polynomial, and we will learn how to get such an interpolating polynomial. So ito yung pang-approximate ko sa sin x, and if you see, if I plug in pi for all x's that you see on the right-hand side, I'll get the exact value of sin pi, which is 0. So ibig sabihin, the second method, the interpolating polynomial, look at this. I only use 3 terms, right? Tatlong terms lang, cubic polynomial lang. Pag pinlog in ko si pi kay x, makukuha ko yung eksaktong 0. But here, in the Taylor series expansion, I used 100 terms. It's a degree what? It would be a degree 199 polynomial. Pero nakuha ko palang na sagot ay 3.52 times 10 to the minus 16, which might be good enough kasi 16 decimal digits na yung accuracy niya. Pero it was beaten by the interpolating polynomial who gave me the exact answer 0. But that case is specific only for x equals pi kasi I designed the interpolating polynomial to approximate pi exactly. All right? But you see here, even if we did the calculations by hand, the Taylor series expansion will still give us some errors. Kasi inherently on the design of the series expansion, there is an error involved. Kasi again, the exact sine function is a summation until infinity, but based on our design of our algorithm, we decided to truncate it down into a finite number of terms. So basically, even if you do it on a perfect computing machine, merong theoretical error na involved pa rin. Okay? And in fact, the error involved in the Taylor series expansion can be bounded. So in terms of the number of terms you used, if you remember from Math 36 or AMAT 152, you probably have encountered there that the error in any Taylor series expansion is the first term that you truncated. So kung ang kinonsider nyo lang sa Taylor series expansion ay hanggang nth term, yung error ay always bounded by the n plus 1 derivative of your function times x to the power n plus 1, but the derivative is evaluated at a number c on the interval being or near the center of expansion. So basically, kahit ipagawa mo sa perfect machine yung computation ng Taylor series expansion using n terms, kahit i-compute mo siya by hand, eksakto, wala kang approximation na gagamitin, meron pa ring error na inherent dun sa method. And that's what we call the theoretical error. Now, in the second type of approximating function that I gave you, the interpolating polynomial, we will learn later that the error, the theoretical error involved there is something like this, which is a little bit similar to the error in the Taylor series expansion, pero medyo kakaiba lang yung form. So, as I mentioned, may encounter uli natin itong mga terms na to. So when we discuss interpolating polynomials, I probably will say something about the theoretical error for this method is this, or we will derive the theoretical error. So I don't want you to get puzzled what is meant by theoretical error. It just means ano yung error na inherent dun sa method na inimbento natin. Okay? So that's the second source of error. The third type is round-off error. Ito na yung error na nangyayari sa loob ng computers. Again, computers are finite machines. So, ibig sabihin, pag meron kang in-input dyan na number, hindi niya i-consider yung buong number na yon. It will depend on its memory capability or on its hardware, right? So, some machines does truncate it to a large number of decimal digits, some with just limited capabilities. So halimbawa, kung may papakompute ka, gagamitin mo yung calculator na pangtindahan. So if you compare your result with the high-tech IBM or top-of-the-line computers or laptops nowadays, we expect better result from those top-of-the-line laptops because we expect them to have higher memory and higher arithmetic embedded on their system compared to the pangtindahang calculator. So, but usually I ask my students to do this exercise, rounding and chopping arithmetic to approximate, say, P of 2.19. The polynomial P is given here. So, yan yung polynomial P. Okay. Then when you say three-digit rounding, ang gagawin mo ay ipa-perform natin yung operations one at a time, pero every after step, lagi ko lang siyang i-round into 3 digits. Okay? So probably you can try it on your own later, but if I can start it here. So, di ba, evaluate ko yung P of 2.19. Supposedly, plug in ko lang yung 2.19 sa lahat ng x's na nandiyan. Pero I'll start doing it as if I am a computer. So first, the computer will evaluate x cubed, right? Now, to evaluate x cubed, kailangan ko yung 2.19 times 2.19 times 2.19, right? Yan yung instruction natin sa computer. Pero ang gagawin ni computer dahil siya ay isa siyang finite machine, ang gagawin niya muna yung 2.19 times 2.19. So let me open my calculator. 2.19 times 2.19 is 4.7961. Right? Yun yung eksaktong 2.19 times 2.19. Pero dahil yung computer ko dito ay inassume ko lang na 3-digit rounding arithmetic lang, ang kaya niya lang i-store at any given time on its memory would be 3 digits after the decimal point. So instead of taking 2.19 times 2.19 as 4.7961, yun yung exact na 2.19 squared, tatanggalin ko lang sa 3-digit rounding arithmetic, tatanggalin ko lang yung dulo. Kasi 3 digits lang yung allowed. So what will happen after the first step is that the computer will say, oh, the next problem I need to solve is 4.796 times 2.19. Okay? And then the computer will again perform the multiplication, 4.796 times 2.19. Ang sagot ay 10.50324. Pero again, that has 5 decimal digits. My computer can only store 3 decimal digits at a time. So that means my computer, or this primitive computer here, will output 10.503 as the value for x cubed. And that is in contrast to what the actual value of 2.19 is. So 2.19 cubed is 10.503459. So the truncation error here, or the round off error, is 0.000459. So which 0.000459 yung na-truncate o nawala dun sa calculation. All right? So that's basically what round off error is, or the truncation error is. So may dalawa lang klase, rounding and chopping. Yung rounding, ang ginagawa niya ay halimbawa meron kang 1.4658. Kung 3-digit rounding arithmetic, titingnan mo yung pang-apat. Yung pang-apat ay 8, which is greater than 5, so kailangan ko mag-round up. So basically, in a rounding arithmetic, it would be 1.466. Now, in a chopping arithmetic, i-disregard niya lang to. So ito yung rounding, nag-round up, depende dun sa dun sa first digit to be truncated. So ito yung rounding. Sa chopping arithmetic naman, wala siyang pakialam gano'ng kalaki yung pang-apat na decimal digit. I will just chop everything after the 4th decimal digit or after the 3rd decimal digit. So in a chopping arithmetic, this becomes 1.465. So yun yung pinagkaiba ng rounding versus chopping arithmetic. But essentially, that's the gist of it. Round of error, siya yung nagagaling sa computer implementation. Computers, being finite machines, cannot handle infinite decimal digits. So nag-round lang sila or nag-chop or nag-truncate according to their hardware capability. All right? So pwede nyo itong paglaruan later. And then I usually ask students to compare the values you get from a 3-digit rounding and a 3-digit chopping arithmetic to the exact value of 1.685159. So pag in-evaluate ko yung P of 2.19 exactly, I'll get this number and I'll ask them to compare this. And the point of that exercise is for also for me to check if they learn the concept of relative error. Okay? Kasi sabi ko na kanina, it's better to always describe your errors in terms of relative error. So pwede nilang computein yung error from a 3-digit rounding arithmetic and compare it to the relative error from a 3-digit chopping arithmetic. So if you have time later, probably you can play with it. And the point I'm trying to make here is iba to dun sa dalawang previous na errors, right? So that's why we have 3 classifications. Yung unavoidable error, hindi talaga natin siya kayang i-avoid because those are the uncertainties in the input. Second, theoretical error. These are from the methods themselves. Pag nag-design ka ng algorithm, nag-design ka ng method, laging meron theoretical error doon kung hindi naman siya designed to compute for the exact thing. All right? And then the third type of error, round of errors, these are due to machine implementation of certain of your algorithms. So aside from theoretical error, meron ka pang round of error na kailangang i-consider. So these are 3 errors that we should be wary about whenever using numerical algorithms and implementing them on a machine. Maybe I can skip this part. The next slide talks about floating point number system. Ito lang yung mga kinagamit ng mga computers or how computers define their numeration system. Usually base 10, base 2, or base 16 yung ginagamit ng mga machines. Pero yeah, if you want to read more on these, I think hindi naman natin to masyadong kailangan. So if you want to read more about this, so you can consult the work text. There's a detailed discussion of floating point number systems there. Okay, so medyo mga technical details, we can skip here. Good question, Angelo. For us, hindi na natin isasama sa bilang yung whole number. Pero ideally, ino-normalize pa supposedly natin siya. I mean, susulat natin siya ng ganito. Sort of in scientific form. So, or in scientific notation, 0 point dot number, then times the base raised to an exponent. So, yun yung parang technically yan talaga yung nangyayari in a machine. Pero dun sa exercise kanina, to make it simple, hindi na natin isasama yung whole number surrounding. Kinonsider ko lang yung decimal digits. Pero in actual machines, what happens is if you input, say, pi, 3.1415.92654, halimbawa, so dot, yan yung pi. So dun sa simplified arithmetic na pinakita ko sa inyo kanina, kung 3-digit rounding arithmetic, simplified version, ang gagamitin ko sa computations ko ay 3.142 para kay pi, right? Hindi ko sinama yung decimal digits. Yun lang yung pinapagawa ko sa mga estudyante kapag on paper nila gagawin. Pero what happens inside computers is this. They first normalizes it in sort of the scientific notation that we use. Here, I'm assuming base 10 na lang yung gagamitin ko para mangyayari, yung input, makikita siya ni computer as 0.314159264 times 10 to the negative 1. And then magte-take into effect, halimbawa, 3-digit chopping arithmetic yung gagamitin ko. So pag nasa normalized form na siya, 3 decimal digits lang yung makikita ni machine. So hanggang dito lang. So either chopping or rounding arithmetic yung gagamitin niya. Ang nasa storage ni computer for the number I inputted as pi would be just 0.314 times 10 to the negative 1. Ito yung i-store niya. Okay? So, yeah, thank you, Angelo, for pointing that out. Yeah, ito yung technically nangyayari sa machines. Kaya wala na tayong tinitingnan whole numbers. Kasi isusulat niyo yon in scientific notation. Alright? It depends. Here, I assume base 10 lang, pero some computers do it base 2. So, binary lang yung ginagamit nila. So, first, i-convert mo muna to sa binary, tapos mag-move ka ng decimal digits. And then, yung pang-multiply mo rito ay yung base numeration system din. Other computers use a base 16 numeration system. Kaya lang may effect din yung base nung numeration system na ginagamit. So kung makikita nyo dun sa floating point numeration system, meron siyang 4 na parameters. So yung mga parameters niya, beta yung base, k yung number of digits allowed. So ito yung parang 3-digit rounding arithmetic na binanggit natin kanina. And then m is the minimum exponent in the normalized version. So ito yon. Si small m, yung maximum value, yung minimum value ng exponent e. And then big M is the maximum value of the exponent. So if you want to be technical about it, ito yung nangyayari talaga sa computer. Kailangan mo yung base ng numeration system, be it binary, decimal, hexadecimal, or base 16. Tapos meron kang minimum and maximum number for your exponent of the base. Okay? I hope that answers your question, Angela. Admittedly, yung first example is a very simplified version of a floating point numeration system. But the whole point of that first exercise is for you to understand ano yung nangyayari sa computer without dealing with the change of base and then yung exponents pa as what will typically happen inside a computer. Okay? I hope that makes sense. All right. What's next? Okay, so you can forget about introduced and propagated error. The gist is yun na rin nasabi ko kanina. And I usually cap off the meeting by asking my students to analyze the propagated error in the 4 basic operations. Kasi na-derive na sa klase, or supposedly diniderive namin sa klase, ano yung error na napropagate sa pag-perform ng addition, multiplication, or division in a computer. So diniderive namin yun. I think in the work text you can see the propagated error for the 4 basic operations. And you see that it depends on, I think it depends on really the value of k. Ilang digits yung allowed dun sa numeration system. Okay? But I don't think we'll need to delve into those details in Math 174. This should have been covered in AMAT 152. But again, I don't want you to be blindsided. Pag sinabi kong round-off error, yun yung nangyayari dahil sa machine implementation. Okay? Now, I should be dismissing you right now kasi 12:20 na. Pero okay lang ba if I stay until probably 10 more minutes? If you need to go for your next class, you're free to do so and just watch the remaining of watch the recording. I hope I'm still here. Na-disconnect daw yung tablet ko. Pero I'll try to reconnect. Aha. Okay, great. Thank you so much. Though na-disconnect yung tablet ko. So, screen share ulit ako. Nahirapan ako mag-project kasi gusto ko on a second device yung pinoproject ko na PDF. So, hindi ko magawa yung usual sa Beamer na may reveal effect. So, kaya medyo, sorry kung medyo maraming nangyayari pag nag-shift ako from one slide to the other. But I love this app kasi pwede ako mag-annotate over. Though na-repeat yung purpose kasi delayed yung annotations. But anyway, So let's continue. Thank you for allowing me to stay over time for probably 10 more minutes. I want to talk about the Bachman-Landau big O notations. We might be using this also as well. Na-encounter nyo na ba to sa AMAT 152? So these are the big O notations, big O of n, big O of n squared. All right. So essentially, just to recap, so pwede na lang pala natin tandaanan. When you say a function is a big O of another function, that means that the function inside the big O is an asymptotic upper bound for the function f. So kailan nagiging big O ni G si function f? That will happen if you can find two constants, a constant C and a constant N naught, such that after N naught, C times G becomes an upper bound for the function f. Kaya tawag sa kanya ay asymptotic upper bound. Upper bound dapat mas malaki si G or yung multiple ni G kaysa kay f, not necessarily for all numbers in the domain, but starting from a number n not until infinity. Right? So ibig sabihin lang, in the long run, there is a multiple of G that becomes an upper bound for the function f. So graphically, ito yung sinasabi natin, kapag ka si f ay big O ni G, ibig sabihin si G ay asymptotic upper bound ni function f. That means there is a constant multiple of the function G that will eventually become an upper bound for the function f. So kung makikita nyo dito, si function f, minsan mas malaki siya kay function G. But what happens at the initial tail of the graph doesn't matter. We are after what happens in the long run. So if you see in the long run, after the number n naught, right, yung multiple ni G ay naging mas malaki na kaysa kay f. And if that happens, then we say f is a big O of G of n. Okay? G is an asymptotic upper bound for the function f. So there are two crucial things that we need to look out for whenever we want to prove that the function f is a big O of another function g, right? We need to look for the constant multiplier to the function g and a number n naught starting from which the function cg becomes larger than the function f. Okay? Now, the utility of big O is that it allows us to track running time without going into the ugly details such as constant factors. Kasi makita nyo later yung mga constant multipliers or actually even constant addends, hindi siya nagmamatter sa big O notation kasi they will be defeated by the function of n. Okay? And also in light of these, if we want to get the big O, or if we want to prove that the function f is a big O of another function, we can ignore the terms and the factors that become negligible as n approaches infinity. Kasi ang tinitingnan lang natin lagi, what happens in the long run? What happens when n becomes a very large number? So in that light, we can just ignore what happens, what are those small terms that becomes insignificant or that contributes nothing much to the actual function in the long run. Okay. Now, some quick examples. Let's try to prove the following. Let's prove that 3n cubed is equal to 0 is a big O of n cubed. Again, the idea for the proof is to find two numbers, a constant multiplier n and a starting value n naught. Kung kailan magiging yung nasa loob ni O ay upper bound ni function f. So in this case, probably we can start with a preliminary analysis. So remember, we want to find C and N naught such that, right? So I use this notation for such that, inverted E, such that this inequality is true. 3n cubed is less than or equal to Cn cubed for all n naught greater than n. Right? So yan yung gusto nating ipakita. We want to show that there exists constant C and N naught such that this inequality is true. So this is an existence problem. So ibig sabihin, if you will be able to give me a pair of numbers C and N not such that this inequality is true, then that's done. We are done with the proof. Okay. So anybody, any idea what should C and N not be? Can you give me choices for those constants? Pero at least nare-review kayo sa method of proof, no? Existence yung gusto nating i-prove. So, one way to prove existence results, bigyan nyo ako ng number na nakaka-satisfy nun. Okay? Anybody? Or nawala na naman ba ako sa meeting? Okay, I guess you are just shy to say this, pero yung obvious choice is we take C equals well, I'll take Tristan's suggestion. Yeah, you can take C equals 4. And he said N0 is equal to 1. Well, that's great because if you plug in C equals 4, you got 3n cubed less than or equal to 4n cubed. And this we know this is true for all n, oops, sorry, for all n greater than 1. Okay, so that means actually baligtad yata. For all, baligtad yung sinabi ko. Dapat to ay n not less than n. So kasi si n yung starting point para maging totoo yung inequality. And Tristan's suggestion is correct. You can just take C is equal to 4, and we know that starting from 1 until infinity, 3n cubed is basically less than or equal to 4n cubed. So that suffices. And since this is an existence proof, hindi unique yung C and N not. You can say, okay, bakit kukunin ko yung pinakamaliit? Overkill na lang. So gawin kong 3n cubed ay less than or equal to 1 million times n cubed. And that's still fine. And this is true whenever n is greater than 1. Actually, if n is greater than 0, then that is still true. So it's an existence result, so we don't need to have a unique solution. So the only thing I'm looking for is what is C and N not. So and then you can write the formal proof for it. So I'll skip that part kasi wala na tayong time. But that's basically all that you need. You need a constant C and a constant N not. Hindi ko siya ma-delete. Why can't I delete this? Okay, there you go. Now, another example is 3n plus 2. Any idea for the prelim analysis? So we want to find constants C and N naught such that 3n plus 2 is less than or equal to a multiple of n for all n greater than n naught, right? Okay, so one thing that I usually do is do term by term comparison. So first, I want to find a lower bound for, or an upper bound for 3n. So alam ko in terms of n. So I know that 3n is always less than or equal to 3n, and that is true for all n. Tama? And then C2, I know that 2 is less than or equal to what? It's less than or equal to n for all n greater than 2. Tama? So what will happen is that I am sure that 3n plus 2 will be less than or equal to 3n plus n. Kasi titingnan ko term by term. Ito, mas maliit sa 3, mas maliit or equal to 3n. But 2 is less than or equal to n whenever n is greater than 2. So kukunin ko lang yung intersection nitong dalawang conditions na to. So here I can say this is true for all n greater than 2. Okay? And so this is 4n. So I can take C to be 4, and n is n naught is equal to 2. Okay, but again, you can be you can choose a larger number than 4. So you can take C equals 1,000. That's perfectly fine. N naught is say 10. It doesn't matter. Kailangan ko lang ay existence. Okay. Now, unfortunately, overtime na talaga ako. So you can play with some of the other examples here. I think I have detailed solutions in the work text about these things. So kita nyo siya dyan. And then a lot of exercises on the big O notation there. And then there's a theorem on the arithmetic on n. You can find it there. Bigos compared. And saan ba ginagamit yung Bigos? So probably I'll end at this slide. It's a nice way to calculate the running time for algorithms. Kasi pagka nag-run tayo, gusto nating makita what happens in the worst case. So when n is very, very large, what happens? So if your algorithm is a big O of n, ibig sabihin yung number of operations involved in your calculation is a big O of n. So ibig sabihin, kung ang n mo ay 10 cubes, so kung meron kang 1,000 operations to run, and your computer runs 1 million operations per second, so it will only take 10 to the minus 3 seconds to finish the job, right? But if you are running your algorithm with 10 to the 6, with value of n equal to 10 to the 6, so approximately 1 second lang yung kailangang i-run. Pero if your operation is a big O of 2 to the n, all right, that means we're using the same machine, but with 1,000 operations involved, then 10 to the 285 centuries before matapos yung iyong operation. So basically, this gives us a nicer way or a simpler way in estimating the running time of algorithms. So instead na sabihin ko, bilangin ko precisely kung gaano karaming operations yung kailangan kong gawin. Halimbawa, instead na i-compute ko siya na n cube plus n plus 1 plus 1 half. Halimbawa, ganyan yung plus 1 half. Tanggalin ko yung plus 1 half. Ganyan karami yung operations. Pag ina-analyze mo na yung operation count with respect to machine implementations, pwede mo na lang, wag mo na i-consider yung n cube plus n plus 1 because we are considering things in the long run. So what will happen when n becomes very large? And you see that in the long run, the additional 1 doesn't contribute any consequential amount to the actual value. In the long run, the value, the plus n is insignificant compared to the value of n cubed. So instead of analyzing your operation count as an n cubed plus n plus 1, you can just say, oh, this is a big O of n cubed. And then, yeah, n cubed na lang yung gagamitin natin in the analysis. So that's what I meant earlier when I said that we don't need to keep track of constants or terms that becomes negligible as n becomes very large. Okay. So may example nga ako dito na, yeah. So kung ganito yung nakita mo na complexity ng algorithm mo, so instead of analyzing it using the exact value, makita nyo na in the long run naman yung 566 wala naman siyang effect. Yung 18n, insignificant na yung contribution niya. This term also has an insignificant contribution compared to 871n cubed. And I can forget about the constant multiplier kasi sa big O, nadadrop naman yung constant multiplier. So essentially, instead of dealing with this long expression here, I can just use big O of n cubed. All right. So unfortunately, I think that's all the time we have. Medyo overtime na nga ako, I apologize. But there's still two topics left, stability and convergence. Perhaps maybe since I was not able to cover it, you can do readings on it and then let me know on Wednesday if you have, on Tuesday, if you have any questions about it. Or when we talk about convergence and stability, I can insert a quick review about these two things, okay? But for now, do you have any questions? Okay ba yung ganitong setup? Disregarding my crappy internet connection. Pero how do you think about this setup? Or gusto niyo yung nagbabasa na lang kayo? Okay, thank you, Jeanette, for your comment. Pero sana mag-react naman kayo or magtanong kayo, no? So, okay, thank you. So we'll do this. And then, tama ba? Napag-agreehan na natin na magkahiwalay yung sessions, no? So, paghiwalayin na natin yung session ng section B sa section V. So, yeah, we'll meet dun sa time slot natin. So, para rin maging personalized yung pagtatanong nyo. So, feel free to ask any questions. Hopefully, o kaya mag-react man kayo, pusuan nyo yung, yung discussion or thumbs up or thumbs down so that I'll know whatever, if you have questions or is my message coming across. Or, mhm. Oh, sure. Pwede kong i-upload itong slides sa Canvas. So I'll do that right after the meeting or later today. So just check Canvas out. Hindi na ako maglalabas ng announcement na na-upload ko na yung slide or available na yung recording. Check nyo na lang sa Canvas, okay? Para hindi na rin na-flood yung email nyo. So i-ano ko naman siya, i-update ko naman siya every now and then. Which reminds me, tama ba? Wala pa tayong lab extra on Monday, no? So ano kayang gagawin niyo sa lab? Probably I can ask your lab instructors to review you about stability and convergence a little bit para yun na rin yung magiging parang review nyo. Okay? But beforehand, it will be great if you can read the work text, highlight those things that that are not clear to you o yung hindi nyo naintindihan, tapos pag-usapan natin or pag-usapan nyo sa lab. Okay? Any other concerns or questions? Again, I apologize. I took 8 minutes or actually 18 minutes over time. Gawa naman kasi yung provider ko. No? So anyway, I think that's it for now. So I hope you got something from today. Thank you for coming. Enjoy the rest of your day. Keep safe. And let's see each other again on Thursday. On Tuesday. I'll post the link on Canvas. All right. Thank you, guys. Bye-bye.
Thank
Thank
you,
you, sir.
sir.
Thank you po, sir.